Okay,
Okay.
well, feel free to get going whenever you like.
Yeah. So thanks for coming along. For anyone that's watching online later, thanks for watching this. I'll be doing a short presentation just regarding my honours project, and that is developing device drivers in Rust. So it's going to be a presentation format, and presentation will take up most of the time, roughly 15 minutes. At the end, well, close to the end of the presentation, I have a 1 minute video demonstration that I'll describe I'll discuss that throughout the presentation, and then at the end we'll open to 5 minutes of questions. So again, thanks for being here and watching along. So device drivers, the fragile. What might become clear during this presentation is that I've based this presentation style on the 9-Inch Nails album, The Fragile. I think it's actually quite a good allegory for how I feel about the state that drivers are in. The Fragile is an album about, personally, it's about confusion, it's about damage, it's about things not quite being right, from what I understand. So personally for me, the style feels like a bit of a fit for how I understand drivers. It might not be totally right, but from my point of view, my perspective, I think it's a good fit. So a little bit of a background on device drivers. They're found within a majority of operating systems, not all. Well, probably all, but they control peripheral devices, work with the kind of underlying hardware. You plug a mouse in, it controls your mouse. There's protocols and everything between the mouse and the hardware. It also kind of provides extensions to the operating system as a whole. Your file, sorry, like ext4 and NTFS, all your file system types, sorry, they'll be implemented typically as drivers or extensions, dependent on how the operating system refers to them. Again, from my perspective, drivers are a bit of a necessity. They suffer from a few issues that have dangerous consequences. We'll get onto that later on. The most major problem that I've identified is that they continue to be written in C. C was originally developed by Dennis M. Ritchie and co. Between 1969 and 1973. So it is quite an old language, and there are attempts to modernise it. You've got standards and so on, but at the end of the day, it is quite an old language that suffers from issues with memory safety. Memory safety, as a short description, with which I'll expand on later, it can lead to critical vulnerabilities. It's mostly present in C, C++, and assembly, but isn't necessarily exclusive to these languages. So the project aim, the original intent was to create a kind of generic USB mouse, but kind of recent findings have found that the Rust for Linux project, it's maybe not quite at the stage where it can be picked up and that sort of task can be performed. I think if I wanted to walk out of this with a USB driver, there would definitely need to be a lot of work, not just implementing the driver, but implementing the libraries and so on, the background systems that driver would depend on. The aim, it hasn't changed majorly. It's kind of shifted more to highlight the benefits for Linux by using what we'll discuss next. So the aim has it's been shaken up a little bit, but it's not changed majorly. But at the end of the day, there is driver development happening. So Rust. I guess what I should talk about is the Rust for Linux project. It's one of the main components of this project, especially with regards to development. As a bit of background, it builds on groundwork that was originally laid by Alex Gaynor and I believe Jeffrey Thomas in 2019. They presented using Rust within the Linux kernel. The project Rust for Linux itself started in more 2020 by Miguel Ojeda. It was recently incorporated into Linux with kernel version 6.1 and beyond, with the aim of introducing a new system programming language into the Linux kernel. Development is currently ongoing. There's a lot of additions, and they do have a Zulip chat, which I believe is open to anyone. They have their own mailing list, similarly to the wider Linux kernel, LKML, I believe. And they have monthly kind of discussions between community members. Talking about Rust itself, which is the main component of the Rust for Linux project. It's a more memory-safe language. It's relatively young. It's a system programming language, as I said, focused on memory safety. It was originally invented by Graydon Hoare, who released the language in 2015 after, I believe, a few years of development. It was then picked up by Mozilla. I can't remember the date exactly, but it was picked up a few years after release. I'm not exactly sure, but it was eventually picked up by Mozilla, wherein development kind of expanded and a lot more people were onboarded onto the project, and it's kind of grown into what it is today. It's got several features. Rust has several features that are really attractive to this project, of improving drivers. It's got a powerful compiler with a strong typing system. It also enforces good code practice. So if the compiler picks up an issue that's common, it knows how roughly to solve. It will describe it to you. Apologies. In its feedback. It provides clear feedback. Old code can benefit from new optimizations. There's actually a lot of examples of Rust crates. That's their term for libraries. A lot of Rust crates are complete. They don't really need a lot of change, and they're just going to continue benefiting from new updates to Rust. It implements ownership, a borrowing system, and lifetimes. And that basically ensures that all object references are valid. It's a very good way of ensuring memory safety and so on. Although it's not a perfect language to some, it was criticised by Bjorn Strostrup, who said, every safe language, including Rust, has loopholes allowing unsafe code. As much as that is valid criticism, it's not the worst thing in the world. It is a bit necessary. The unsafe system allows interaction with system resources, and the underlying hardware isn't mutable, so it's necessary to actually interact with hardware. Recently, it was discussed between myself and others on this project. Haskell similarly has backdoors. So the best way to put it is that having a backdoor such as unsafe or Haskell monads, it isn't some kind of gotcha where it automatically invalidates the language, and it's actually sometimes critical. Without the Haskell monads, you wouldn't have your Haskell I/O system. So there we go with that. In regards to memory safety, it can be defined as accessing memory, typically outside the bounds of a data structure, which then provides a vector to attack from to conduct further exploitation or attack. It was fine. Sorry. The this is why memory safety is so important to this project. Memory safety vulnerabilities aren't as well defined as other vulnerabilities. This was found by Google in their Android 13 security blog. Memory safety vulnerabilities can actually be more flexible and therefore are commonly used as attack surfaces rather than direct attacks, if that makes sense. On the left, you'll see a table of statistics that I made up from an article by Alex Keir, which demonstrates kind of percentage of vulnerabilities. This is from 2020. These things might have changed, they might have lessened, they might have gotten worse, but it gives a general idea of how common these vulnerabilities are, as well as how severe they can be. As is written, each of these statistics is from a large code base with millions of lines of code, and all are written in C or C++, and includes a wide range of memory unsafe related issues, use after free, double free, overflows, etc. The average percentage of vulnerabilities of these code bases is 71%, which is fairly critical, especially if you're talking about such large code bases as these. Next, moving on from key points, I'd like to talk a bit about kind of the work I've been doing, starting with progress. I've improved interim report content. I've been working on dissertation writing, roughly halfway through. Development has continued, but it's obviously had a bit of a hurdles previously discussed. That's yet to be resolved, and I'll expand on this in my next point. Alongside these points, there's also been industry input. Reached out to several people within software engineering, development, Rust. Likely the most important, most helpful have been Alex Gaynor, Miguel Ojeda, and Jonathan Blow. Gaynor provided me with a pull request for the Rust for Linux project, which was trying to implement the USB protocol and related libraries. Ojeda actually gave a lot of information. He was very interested in the project and sent over a blog post that he had written about the history of the Rust for Linux project. So you can thank him for the Rust for Linux details in this. Jonathan Blow, we had barely a conversation, but he was very descriptive. He gave me a Xenix ATC talk regarding operating system design and implementation. It's quite interesting. He also brought up the point of exokernels, which I'll talk about later. But all three have definitely helped with the project, and I'd like to thank them, whether they watch this or not. They've been very helpful. In terms of development, I have enabled Rust support on a Linux 6.1 plus machine. USB support is under development within Rust for Linux. It is not at a perfect stage. To be honest, it's not the best, but it is what it is. To expand on that, not all the kernel subsystems are implemented from Linux, so the conclusion seems to be that the Rust for Linux project is quite young, but it has a very bright future. When all of those subsystems are implemented and other improvements have been made. Our demo at the end will be a compilation and execution of a simple hello world driver in Rust. It's written in pure Rust and is running on the previously mentioned 6.1 machine. It is virtual. I've struggled to get Rust support running on physical hardware, but for the sake of the project, I've just had to keep moving. In terms of findings, quite possibly the most interesting are from Google and Android 13 and regarding the exokernel that I mentioned earlier. With Google and Android 13, they started implementing a lot more of their Android 12 and 13 components in Rust. They recently, I think it was a few months ago, found a significant drop in memory safety vulnerabilities and severity. Apologies. Memory safety issues now account for 35% of total Android vulnerabilities, which was previously 76%. And as mentioned before, Rust was adopted in Android 12 as an alternative to C and C++. So the drop coincides with less memory unsafe code, more code written in Rust, with Android 13 being the first released, where most of the new code is in a memory safe languages. As of their security blog, I haven't chased this up. I don't expect it to have changed. There have been no memory safety vulnerabilities found in Android Rust code. The findings from Google is that Rust allows them to optimize security and system health with less compromises. Developers don't need to think about trade-offs as much. So generally it seems very beneficial. They've lessened what is a high percentage of their bugs, and it seems to be going very well for them. In terms of the exokernel, this is a very interesting concept, and it kind of it takes the point away from programming languages and thinks more about operating system design and implementation. At that USenix keynote that Jonathan Flo gave me, it's titled "Time for Operating Systems to Rediscover Hardware," and the wider point is that some in OSDI feel their field has a lot of opportunity but not much interest. They feel that hardware should be considered more carefully. That is cutting it short. It was very in-depth, but that's the general gist. They feel that operating systems can be designed better. There's a better way of doing it. And an example of this is the exokernel. The exokernel basically wants to break down as many hardware abstractions as possible, force as little abstractions, but still make them available as needed. So all of these hardware abstractions that pre-exist are put into untrusted libraries, which can then be called from. But generally, software is in charge of its own memory control, memory implementation. As I've written there, it would be in charge of its own paging, scheduling, context switching, and fault handling. The benefits of this is that it would improve performance, it would improve efficiency, development, and testing. But the drawbacks would be less consistency and a kind of more complex design in terms of interfaces for an exokernel. So it is one of those things where we need to see how it goes. I don't think it's a popular idea or a popular design choice in operating systems. I'm not sure if it's been I'm not sure if it's been widely used, but it is apologies, an alternative that we can consider if the whole programming language thing doesn't really work out. So yeah, the general design philosophy is to expose as much hardware as possible. To expand a little bit more on development with a funny little graphic, I'd like to detail some steps in installing, configuring, compiling Rust. So generally you would start by recompiling an existing kernel, especially if it's not up to date with Linux, at least version 6.1. You would recompile it to that version. From there, you would install and configure Rust. This isn't an exact way of doing it. All these, well, a couple of these steps are interchangeable. I've found that compiling first and then installing Rust leads to less issues and is a bit more streamlined. After configuring Rust within your 6.1 box or machine, you'll recompile this 6.1 kernel once again, but with Rust support enabled. And there's a few things you need to enable in order to do that. There's a few steps that you need to carry out, which is why it's necessary to recompile so often. After this new kernel with the Rust support is built, you can enjoy your new Rust kernel, and it's I guess the best way to describe it is pick up and play. It's immediately available. You don't need to mess around too much. It's just a case of recompiling a lot, which can be time consuming. So I guess before we move on to our demo, these slides were, as I mentioned, inspired by The Fragile by 9 Inch Nails. So images used in the background are credited to David Carson / 9 Inch Nails. I'm not entirely sure about the ownership of those photographs. So thank you to them for their art and so on. We'll move on to our demo now. So as we can see here, we have our Rust code written in purely Rust. The structure is fairly similar to a C driver. The common way of compiling this would be a makefile, as you can see here, and that will generate a .ko file. This ko file, its a Windows equivalent would be a DLL, I guess is the best way to put it. This is your driver in its compiled form. You would use insmod to insert the ko file and rmmod to remove them. And then dmessage is a command that allows you to peek inside kind of kernel messaging. As you can see here, there's a little error, but it shows the hello world Rust running. So the hello world actually represents the entry point, I guess you could say, and the goodbye is the exit point, which is all kind of handled automatically by Rust. So yep, going back to that's our demo. Thanks very much for listening or watching, and I'd like to now open up to questions.